So our speaker for today is Mattia Martini, and he will give us a PDE perspective on harmonic measure. Please, Mattia.
Hi, thank you. This is me saying hello. So this is me. Welcome, everyone. Thank you for having this seminar and to be here to hearing what you have to say. So the topic of today is yes, harmonic measure, but not in the essence of the thing, but we will let's say go into some relation with PD, and so we'll try to be a little bit more detailed about a way to deal with harmonic measure, but more in detail with harmonic function through probabilistic technique. So the core is basically to relate the PDEs and some probability stuff. Wait a minute that I have to let people enter in the waiting room, from the waiting room. Okay, so now we have other two guys, so ciao Tanne, ciao Samonzani. So going back to the goal of today, let's try to link mainly the Dirichlet problem, so this quite famous problem in PDEs, and the Brownian motion. This has been already a little bit said by Francesco the last time, but now I will do not too much detail, but some detail. So let's start with some recap and notation to get a little bit used to the everything. So chapter 1, recap and notation. So, of course, the focus of what we are going to study is the Brownian motion. So the last time the Brownian motion has been introduced as a Gaussian process with independent increment. And so basically this is what we did. So Brownian motion. We will use the notation like WT with t greater or equal than 0 or B. Both of them, each time I wrote something like this is a Brownian motion. So this is t greater than 0. These are devalued. So for each t, this guy belongs to Rd. And basically a way that you have to imagine this guy is just a sequence of random variable indexed by the time, or a random trajectory in the time. So you can select something like this. So here we work in dimension 1, for instance. And here we have the trajectory of Brownian motion, which is something like this. Here you have the time. Here you have R. And basically, this guy is WT because it's a function. And since it is stochastic, it depends on omega. So under all the things, there is a space of probability omega FP. So there is a probability measure on this space omega, and that's it. So this I won't focus on this detail, but it makes sense to say at least once that we have a probability space. So omega FP. So basically, what does it mean? Random process. Well, for what we pick an omega, then we have this trajectory. We pick another omega from this capital omega, and then we can obtain another trajectory, something like this. Now here, usually what we need to focus on are Brownian motion, not starting from 0, which is a usual definition that is given in probability, but starting from a generic point x. So the notation will be this one. So I will put a small x as an apex to highlight the starting point of something. So here in this case, there is still a mistake because here there are two Brownian motions starting from different points, but they should start from the same one. So I will do like this. And so this is a very quick example of Brownian motion. And well, the important things that we have to keep in mind about this is that Brownian motion has Gaussian increment. So if you take Bt minus Bs with t greater than s, then you obtain a Gaussian increment. So this is why it is called Gaussian process. And the variance here is t minus s times the identity if we are in a multidimensional environment. So here t greater than s. And the increment are independent. So basically what happened after a certain time moment is independent from what happened at that time. So okay, so I won't go too much into this. And last thing that I should recall is that we assume that it's continuous. So each of this trajectory are continuous. So it's continuous. So we start from a small point x, then we evolve in the time continuously, so no jumps. And okay, so this is just for fixing the notation about Brownian motion. Just to okay, be complete, let's just write down a useful notation, which is actually a sort of theory, but don't want to go into the theory of stochastic integral. But let's recall that I will give you as a sort of way to denoting stuff, but there is actually theory behind this. So what I'm going to write down now is the definition, the stochastic integral way to write down the Brownian motion. So it's like a stochastic integral. And here is basically a notation again. And we write down Bt of x, so the Brownian motion at time t starting from small x. And basically we write down as an integral, so in an integral form. So small x, which is the initial point, plus the integral from 0 to t. And here, the natural thing that one, playing thinking about heuristic or symbols, the thing one could imagine is that what is the best way to write down this guy? It should be 1 times the dx. So take this just as a notation, but this guy can be defined in a proper way. Makes sense, is a random variable for every t fixed. This is a s, of course. So this is called the stochastic integral of 1 in this case with respect to the Brownian motion. So stochastic integral of 1. And okay, makes sense, but we don't want to go into the details because it's long. But we just keep in mind this notation. And okay, here is natural that this guy is just, it follows the usual rule of integration, at least in this case, because in more general cases does not. But at least when we integrate 1, what we obtain is exactly what we are expecting. So the integral of bx evaluated in t minus bx evaluated in 0, which is actually x. And so we obtain the equality. So this is a way to denote, to rewrite the Brownian motion. And Another way, still from a notational point of view, but again, it's cool to fix it now, is to write down this relation in differential form. So here we talk about stochastic differential. So this is purely a notation, and when we write down this stochastic differential, it is meant in integral form. So when we write down dbt x equal to 1 times, of course, here is a sort of tautology, but one can add stuff. Then this is meant in this sense. So d0 x equal. This is this one. Of course, here is a sort of, again, more useless way to represent things, but in a minute, I will show you a more complicated formula of this kind, the so-called Ito formula. And so in that case, we will refer to stuff in integral form. So the part in the B will be of this kind, and the part in the S, you will see that is also an integral. Okay, so couple of notation. Let's introduce the first key object. Again, it has been presented the last time by Francesco, but we need to restate here in order to have everything. And this is the so-called ethos lemma. Ethos lemma. What is ethos lemma? Is a sort of chain rule. So this is a way to provide to compute the stochastic differential in the sense of the composition of a deterministic function and something random, a random process. So why this should be important, why this is important and why this is not trivial? Again, this is related to the fact that this sort of integral behaves like normal integral if you integrate one, but for instance, if you integrate something more complicated, then you start noticing that extra terms appear in the computation. And as an example, I will just write down what happened in this case. So let's just integrate the ds in the ds 0. Let's start from 0, so we will not have the initial condition part. In this case, what one can expect is that, I mean, from the standard integral, what we are expecting is something like 1/2 bt to the power 2. So this is what will happen if this would be just a standard integral, so with respect to a proper function, which is increasing with finite total variation, or if you just substitute b with x, this is what will happen when we integrate a standard x with respect to the back measure. But here, thanks to how is this stochastic integral defined, and again, I want to define that for you, but just trust me. This guy is equal to 1/2 b square t, but then there is a sort of correction, which is actually of order 1/2 t, if I remember, or something like that. Ale, help me. What is the?
Yeah, it's like should be.
I remember. Okay, I at least need another guy from probability that don't remember what is the real part, the correction of this integral. But yeah, the fact is that here we have an extra term of order t, something like that. So something containing t or t square. So actually, this is just to say that, okay, if we integrate 1 with respect to the b, then we obtain the Brownian motion, and that's it, that's fine for this kind of representation. But things becomes more complicated when we start to integrate processes which are a little bit more complicated. So not just the usual rule of integration. And so since we are using this notation, not the same rule for differentiation, and so at the very end, we cannot expect that the usual chain rule will work. And for chain rule, I mean something like this. So this will be the usual one. So u prime xp times. This is the usual. And this does not work in our case. So what we can do in this case, well, we can prove the ethos lemma. So it's the real formula for this case. And okay, let's write down just for the Brownian motion. So let us take a function f, which is from Rd to R. And let us take in C2 of Rd, so twice continuously differentiable. Then what happens is this. So we take the function fwt, and this is equal to f of x plus integral from 0 to t, the gradient of f. Now, don't be scared, it's just the first derivative. So if you are in 1D, this is just the first derivative of f. And f is deterministic, so this is deterministic derivative. Evaluated in, okay, let's use b because I will use b for the entire discussion. So evaluated in b times the differential, and this is a stochastic integral of this kind. So it's defined, well defined, but okay, it's not trivial, it's the one with 1. And then, and this is the normal part, actually, the one that behaves like the standard chain rule. Then we will show it in a while. But then we have to add the correction we see before. And this is actually, oh, here we have a t-squared, no. And okay, the correction in this case is just 1/2 integral from 0 to t, the Laplacian of f in ds x ds. And this is basically the extra part that is generated by the stochastic part, and it's called Ito correction. And this is due to BS, so the stochastic part. So this is the chain rule using the notation we introduced before for the stochastic differential. One can read this as the FWT, again, come on, B x equal to gradient of x dtx times d plus 1/2 btx in the t, and then the initial condition, so f d0 is equal to f of x. Okay, so this is the more involved differential notation, so a little bit less trivial than this one. And again, this is meant in this integral form. So the t part is just an integral with respect to the time in the Lebesgue sense. And here we have the stochastic integral, whatever it means. And okay, here what you can see is that actually we have a first order part which behaves as the usual chain rule. So the derivative of f times the differential of what we have inside. So gradient of f times the b. But then we have this second order correction. And for second order, I mean the fact that here we need the Laplacian, so it contains the second order derivative of f. This is why we are asking f to be C2 and not C1, even if we are just computing one derivative of f. And this part is basically the key point of all the discussion I'm going to present to you today, and the key point of the relation among the Brownian motion and the Dirichlet problem, which is actually a PDE involving the Laplacian, and everything is encoded in this part. So, very long introduction. Now let's go a little bit to, let's state what we want to do, and then let's go into that. Just a remark that we will use later, and that I forgot, is the so-called martingale property of stochastic integral, but again, don't be precise on that, but what happens usually is that if you take the expectation, so expected value of this guy, this things is usually, so under nice hypothesis of f for on f, for instance, f bounded with gradient bounded, this is equal to 0. F belong to C1b. And this will be important for the computation at the end of the lectures. But yeah, this is just say that the object you obtain in this way, which are random variable, so there is a hidden dependence on omega, so random variable. So it depends on omega, you can take the expectation. And what usually happens is that if you have an integral of this kind, its expected value is equal to 0. So it's behaving nicely in mean at least. And okay, so these are sort of things we need. Something unclear, I think more or less everything, but at least you have in mind this kind of notation. So when I wrote stochastic integral, we have to think about an integral that sometimes behave good, sometimes behave bad. If I write the differential, we have to think about them in integral form. And if I write the expectation of an integral in the B, you have just to say, okay, it's 0, more or less. So this is to summing up the tools from this introductory part. And so the goal of today is to explore the relation between or among between these two problems. So on one end, we have the Dirichlet problem, which comes from very far in the past. And it is actually related to the distribution of the potential of a charge in a certain domain. And this is actually gradient of Laplacian of u x equal to 0 if x belongs to a certain domain. So D is a domain. I will be a little bit more precise later. So we ask that the sum of the secondaries, so the trace of the gradient with the trace of the Hessian is equal to 0 inside our domain, and we prescribe the value of u at the border. So u is equal to a certain function phi if x belongs to the border of D. And okay, this is the Dirichlet problem. What is our claim? So what we want to show is that in some way, we have a probabilistic way to represent and to find a solution to this problem which is different from the usual one in PDE. And the way is this one. So we define a function u in this way. So take the expectation of the condition at the boundary, so this guy, and then compose it with b starting from small x and evaluated at a certain time that we call tau. What is tau? Tau is actually the stopping time we want to study in the harmonic measure setting. And basically, tau is, I will call it tau d, at least at the beginning, is the hitting time. And to be precise, also, it depends on small x. So I will just do it once and then I will drop the notation. So xd is the hitting time of the boundary of d of the x, which mathematically can be written as the infimum over the t positive, such that it belongs to, let's say, the complementary. Here we take the open, but again, we will go in detail later. This is equal to say that bt belongs to the boundary of D. And actually what we are looking for is just take a domain. So this is our D. The black part is boundary of D. Take an X inside the domain, so here. And let's start the Brownian motion. So our Brownian motion start to do Brownian stuff. So blah, 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 blah. And at a certain point, this is guaranteed by the theory. I won't prove that, but this happened with probability 1. The trajectory touched the boundary at a certain time. This is t that increased. So it just move around the plane. At a certain point, it touches the border of D. This is t. Depend on x, since it depends from the starting point we choose for the Brownian motion. It's depend on t, since on d, since of course if we change the domain, things will change. And to be precise, txd is a random time because it depends on the trajectory we choose for the Brownian motion. So for every omega, we have a different trajectory of the Brownian motion, and so a different value of time in which we hit the border. So td is actually a t dx of omega. And so at the very end, we have this random time. So we have this picture, this guy. So take the Brownian motion, let him evolve until this part. When he will arrive at this point, he will have a value which is random, but which belongs to the boundary of D. So it will make sense to compose it with this function phi, because phi is defined only on the boundary, but here we are evaluating the Brownian motion on the boundary, so it's fine. We obtain this object, which is again stochastic, because here we have a deterministic function composed with something which depends on omega. So this guy's random variable. Let's take the expectation. Recall that everything depends on the initial point. And then what we obtain is a function of x, deterministic. And what we claim is that this guy is the unique solution to this problem under suitable condition. So two different kind of problems. So here we start, we prescribe the boundary condition, and then we let the Laplacian spread the things. here we just start a Brownian motion, let him evolve, then we do some magic, so we compose it with a function, and then we obtain a solution to the same problem. So this is the connection that I want to explore today. And why this is important for the harmonic measure problem? Well, because if we choose the function, the final condition of this problem in a proper way, then we will be able to evaluate the harmonic measure. So let's just conclude on this. So why this is important? This is cool. So if we define mu xd, the harmonic measure, which is actually, let's define it like this. So take a set A. So this is for every A belongs to the Borel set of the borderline, the boundary of D. If we take this guy, the harmonic measure is just the probability of our Brownian motion stopped at T, where T is the one we introduced before, so basically PDEs belong to that A. So here, going back to this problem, we can say, for instance, we take this set here. So this should be our A. The harmonic measure is the probability that if I let a Brownian motion starting from small x, the probability of ending in that set. So this is the harmonic measure in this case, exactly the one we discussed last time. And how to relate this guy with the problem I showed you before. Actually, if we take phi of x as the indicator of x of the set A, so this guy is equal to 1 if x belongs to A, is equal to 0 outside, then what will happen is that what it happens is that ux expectation of this guy b so x, so this is the candidate solution to our problem. This can be written in this way, so expectation of indicator A btx, and okay, basically a computation from probability 0, but I won't do it because it's an integral, but trust me, when you took the expectation of something, of an indicator, then this is equal to the probability of this guy belonging to this set. Difficult, super difficult to speak in this language. So since we have an indicator here, what happens is that this is equal exactly to what we want. So then if this does not convince you, let's terminate part. And this is actually the harmonic measure of A. And so why this is cool? Because we're able to relate the harmonic measure of a part of the boundary with a PDE. So PDE, we are going the reverse, right? So let's start from here, choose as a final, choose as function the indicator. Then, so this guy becomes the harmonic measure. And so at the end, if we are able to solve, for instance, this PDE, then we can have, we already have computed the harmonic measure. So this is a way to look at the harmonic measure through the PDEs, or look at the PDEs through the harmonic measure, because of course it's cool also the way around. So this is basically what is important in this case, and one can do it also in an infinitesimal way, so to obtain not the harmonic measure of the set, but an explicit form of the harmonic measure, but I will go into it at the end of today. And okay, basically here the important thing is that if you look at the harmonic measure of that part through a PDE point of view, what you are basically thinking about is just take a domain. So let's take the square. This is the PDE point of view. Prescribe a boundary condition. So let's put it like equal to 1 here, 0 outside. Then let the Laplacian do its job. So basically the things start diffusing. So here it will be a little bit more intense and then start to spreading a little bit around. So this is what Laplacian do. Remember that here the things must be equal to 0. And when you are looking to harmonic measure of this set, this is A, depending on X, what you say is just, okay, take X here and mu xd of A is just what this function, so this is the solution of the Dirichlet problem, is the value of this function at X. So is this value, which won't be 0 because you are decreasing, but yeah, it will be a function which solves this PDE. So this is how to look at the harmonic measure from this from the PDE perspective. So prescribe the boundary condition, find the solution of that PDE, and then look at small x. Then you will obtain the harmonic measure of A. So you start from A and then things evolve in here. If you go from the probabilistic point of view, is a sort of different way to look at this. So from the probabilistic point of view, you start from X. Again, you have A at the borderline, and then you let your Brownian motion evolve. And at a certain point, you want to just compute the probability of ending up here. And these two guys coincide. So X of t, okay, and they are equal. So two different perspectives. One starts from the border, and then you find your X, and in this way you recover the measure of that segment when you start from X. On the other part, you start directly from X, let your Brownian motion evolve, and then you will end up in the border and compute the probability. So this is the two different point of view. So, and this is quite interesting, I mean. Okay, so cool. We have did this very long introduction. Now let's try to, the goal now is try to make this a little bit more formal, for a little bit more clear. So let's start talking about harmonic functions. So what we need in order to characterize the Dirichlet problem. Harmonic function. I will be quick, I will say, but I will just set a little bit of point and definition we need. So here we say that we will work in a domain D. So when I say D is a domain, I meant like a bounded, open, connected domain in our D. Bounded, open, connected, usually. And okay, when I talk about the border of D, this is just the closure minus D. And okay, so we say that U is harmonic if U belongs to C2 of D, so of our domain, and actually if its Laplacian is equal to 0 for every x belongs to D. So this is exactly what happened in the Dirichlet problem, but without taking in account the boundary condition. So here we are looking just inside the domain, at what happened inside the domain. So, and this is a nice property, way easier to achieve than the property of being a solution to the Dirichlet problem. So this is our kind of function, and then we have the right definition of the Dirichlet problem. So we want to find U, now defined in the closure of D. So we reach the border such that U is harmonic inside. So for x belonging to D. We have the boundary condition in this case. So this guy is equal to phi x if x belongs to the boundary. And moreover, we require a little bit of smoothness. So here, this is called, of course, Dirichlet problem. Here we ask that U is continuous in the U is C2 in the open. Okay. So this is the Dirichlet problem. So the right way of writing down what I introduced above. And okay, so what the last things we need about harmonic function is the fact that there is a nice way to characterize them from an analytical point of view. So since there are not too much PDE guy in the room, I won't stress it too much since you won't notice that, hopefully. But okay, so the thing is that there is a nice way to characterize harmonic function, and is the so-called spherical mean property. So, and this will be a key point to prove the relation, one of the two key points to prove the relation between the probabilistic formula. So, proposition we have that, okay, saying by word, we have just harmonic if and only if mean value property. Mean value property. Formally, what does it mean? Well, if D is a domain, if U is locally bounded, so whatever that means, then the following are equivalent. So U is harmonic on D. So this is what we want. So again, we're not talking about the boundary condition, and this will be the very technical part that I will skip. But at least inside, everything is cool. And well, we have that U is harmonic on D if and only if U has the spherical mean value property. So as spherical mean value property, which means that for every x in D, so fix a point in the domain and take a ball centered in that x, which is again contained in the domain. The domain is open, so you are always allowed to find such a ball. So for every x in D, okay, for every r greater than 0 such that the XR belongs to D, it holds this fact. So your function at the point, so again, take your domain, here you have X, you have that the function evaluated at X is equal to the integral over the boundary of the ball of radius R. Here we start from 0, but because we are translating the things, of U X plus zeta. Here I use this ugly notation, but this is just the normalized measure on the boundary. So basically, this is the Lebesgue measure on the boundary times 1 over the Lebesgue measure of the whole boundary. So we are basically normalizing the things. And so it's the measure over the boundary times 2 pi, whatever it is, if we are in R2, for instance. And basically what we are saying is that take this ball centered in X, this ball has radius, this ball has radius R, but this iPad won't let me do this. Come on. This is like le macchine ribelli. Okay, so you have this ball, and you have that taking the value, the value of U in X can be computed just saying, okay, let's do a mean of the value of U, but around the border of this ball. So you take these values here, just think it in a discrete way, sum of all of them, and then normalize it by the how many they are. So if we do like a mean of U here, this is equal to U of X. And this is quite cool because it works for every ball. So at each point in this domain, you're able to represent U of X as the mean of what happened at U along the border of a ball. And okay, there is also another property, let's say basically the same, but with the entire ball and not just with the border. But since we are looking to eating time of stuff, we won't focus on the volume part, but also that one is equivalent. So if this happens, then you are harmonic. I mean, you can, yes, that's it. I mean, you can also write down without this, I mean, with this other notation, but it doesn't matter. Okay. So this is quite important. I won't prove that because I'm not a PDE guy, and if you're a PDE guy, you know this result. If you are not, just trust me because it's technical to prove and not so funny. And okay, I think that this is all we need for harmonic stuff. Now, once we know this, we can go to the core of today, so to the probabilistic representation. So representation of solution to the Dirichlet problem. And again, the idea is to say that you solve the Dirichlet problem uniquely if and only if u is this guy. Okay. And a first things to do is just to convince ourselves that this should be the right formula. And in order to do that, let's just do some formal computation in order to see that if there is a solution to the Dirichlet problem, then it must be of this form. So, motivating proof. Computation. So let's assume that U is a solution of the Dirichlet problem. So we don't know if there exists any, but let's just say, okay, if there is any, let's take it. So let's U be a solution to Dirichlet problem. That means that these two things happen in the without we avoid the regularity stuff. Then what we can do is just to take U. If U solves the Dirichlet problem, U is C2 because we want to at least in D. So what we can do is to say, okay, let's do the Ito formula of U composed B, the Brownian motion. So by Ito formula, which is again the chain rule to compose a deterministic function with the Brownian motion, we have this part here. So U bxt is equal to U bx0 plus the two terms we read down before. So the gradient of U evaluated in ds in the ds plus 1/2 0t Laplacian of U ds ds. Now, what we can do here, what we can notice. First, this guy is equal to 0. Why? Because U is harmonic. So the Laplacian of U is equal to 0 for every point in the domain. Here, the x is evolving inside the domain, is confinated in D. So the x is a point of the domain. So if we evaluate the Laplacian of U in that point, it will vanish. So this guy is 0 since U solves the Dirichlet problem, particularly because it's harmonic. Here we are not talking about the boundary condition from the moment. Now, the second thing we can do, and here I'm cheating a lot, but let's just do it to convince you, is just to take the expected value and to consider t equal to tau dx, so the heating time of the boundary. So take t equal to tau dx, so the first moment such that our Brownian motion starting from x hit the boundary of D, and then take the expected value of everything. Now, on the left-hand side, what we obtain is just expectation of U dx in tau dx. So this is exactly our guy here. So happy about that. And on the right-hand side, what we have. First, another thing that we have to notice is that this guy is just u, which is deterministic, evaluated at the initial point of the Brownian motion. Because here we have B0x. Small x is the starting point of the Brownian motion. B0 is the Brownian motion at time 0, so when it starts. So this is actually x. And u is deterministic. So this object is deterministic. When we take the expectation, we obtain just that object. So the expectation of a constant is the constant. So u x times, here we have the expectation 0 for the x of this guy here. But, and here is where I'm cheating a lot, is that this guy is the expectation of a stochastic integral. So what we learned at the very beginning of today is that if we do the expectation of a stochastic integral, then it is usually equal to 0. So that usually is the problem, but it works with a little bit of more technical weapons. So what we can say is that this is equal to 0 since expectation of a Stoch integral. And so at the very end, what we obtain is that if we have a solution to our Dirichlet problem, then it must be represented in this way. So ux is equal to this guy here. So this is cool, and this is what is motivating us to look into solution and try to relate the probabilistic, the representation, and the Dirichlet problem in a more strong way. So now that we know that if there is any, then it should be of this form, why do not try to say, okay, let's do the opposite. So let's just define this function and try to show that it solves the problem. If you're able to do that, then we have existence and uniqueness, because the existence is this guy, and for the uniqueness, what we can say is that, okay, take another function, but thanks to this proof, it should have this shape, so they must coincide. So this is the very idea behind this thing. And okay, so I have a question. How much time do I have more or less? Can I go, I think, up to 12, or you have to do stuff?
Yes, yeah.
I mean, or I can stop in a few minutes. Just do the proof and skip some technical part. And I will try to be short. So, okay, now the important thing is that you don't have to do anything in 2 minutes, because if not, I will have to run. Okay, so let's try to write down the proper theorem that's related to things. So here we need a definition before, which is regular point. And this is related to the Poincare-Cohn condition that Francesco presented last time, but don't want to go into that. But we say that a point x0 belonging to the boundary of D is regular. For C, we say if the probability of D x0 is equal to 0 is equal to 1. Now, written this way is terrible, but what does it mean? Is basically say that if we start from 0, if the Brownian motion starts from x0, then he leaves the domain in a at time with size epsilon. So in positive time, it will be out of the domain. So if we must run there, then it will be in this soon, not soon, but immediately. And a classical example is this one. So take a ball, and let's do it properly. Take a ball with a point inside. So our domain is basically, how can we write down? It's basically the ball 0, 1 open minus the center. And here x0 is singular. See, of course, regular, not regular, we call it singular. So x0 is singular here, x0 equal to 0. And why? Well, if we start from here, so we start from a point in the boundary because 0 belongs to the boundary of D, then then we let our Brownian motion evolves, then there is no way to go outside the domain immediately. So just after our departure, and so here there is no way it stays in the domain, and so in this case we have that the x0 is different from 0. Yes. So basically here it is, I mean, TD x0 equal to 0, it means that basically you start and you get killed once you started. So basically if you start in the board, in a distant board, if you start from the border, for instance, if you start from this part, then you can go there and one can prove that actually its probability is equal to 1. It's not easy, but and if you go there, you are in the complementary of D, and so tau D is triggered. So this is an example of this kind of object. Another way to describe this point is the fact that you should be able to build a cone on that point which stays completely outside the domain. This is the so-called cone condition. And here, for instance, is the case here. Here you can build this cone, which is completely outside the domain, but the same thing does not happen inside here. For instance, if you start here, there is no way to build a cone that is outside the domain, completely outside the domain D. So the inside is D. So what we can say is that this is equal to the cone condition. This has been presented in this way by Tramonzani last time. And why I'm stressing this, because the result I will present you holds for domain with a boundary made by only regular point, but for instance, the square is of this kind. So this is a cool thing. So let's go for the final theorem. And so what I was saying is that let D belongs to our D be an open, I mean, be a domain such that every point of D is regular. Then let's take a final condition which is continuous in the boundary. And this is basically the main issue because, for instance, the indicator represented at the beginning are not continuous. So this is the things that broke all what I said till now, but don't focus on that. I mean, there are ways to approximate things. And let the x be the exit time from d of the dx. So exactly what we did before. Then ux equal to expectation of this guy is the unique solution to the problem. So the real connection is that, okay, if we take a cool domain with a smooth boundary condition continuous, then the unique solution is actually the one given by the probabilistic representation formula. And this is quite cool. I mean, it's a nice way to relate the two things, so the probability part and the PDE, and it can give insight from the two field. Now, the proof of the uniqueness, proof of uniqueness, it's easy in the sense that, easy. The correct way to do that is to use the maximum principle. I will want to do that, max principle. Or another way is using the argument I showed you before. So just take a solution and show that it must be of this form. But in this case, one have to fix a little bit the cheating part that I did. So the formula. I mean, with the representation formula, you will see that every solution you take must have this form. So they must coincide. Each solution must coincide with this. So this is the way to do uniqueness. Let's just go a little bit into the existence. And this is the cool part, and it's late, but let's try to do that. So let's prove existence. And I will focus only on the fact that U is harmonic, so I will avoid to think about boundary condition, which is actually the real technical part. So step one, let's just define U in this way. So with our candidate solution and prove that this guy is harmonic in D, which means the Laplacian of U is equal to 0. And to do that, we show that it satisfies the mean value property. So show that U has enjoys the mean value property. That means that, again, for every x in D, for every R positive such that Bxr belongs to D, with that Ux can be written in this way. Okay, now to do this, the main ingredient, which is actually the only thing that basically let things work and is the key point of Brownian motion and this kind of theory, which is called potential theory at the end, is the Markov property. Markov property of B, which is a sort of flow property, which basically means that if you let your Brownian motion evolve up to a certain time, then you stop that and that start again, it's equal to just consider a Brownian motion, another one starting from that intermediate point and let him evolve in mean. Now, writing it in terms of formulas, we can say just let us take sigma smaller or equal than tau, 2 times, that should be random. Let's take this guy. So F sigma, this is omega, then I would explain the notation, but this is the key point of what I want to do, y equal to bx sigma omega. Now, both of these objects are stochastic, and what is this guy? This guy is just the expectation, the condition expectation. How can we look at this? We can just look at this as we do the expectation of this guy, but knowing what happened up to time sigma. So in a certain way, we can look at this. Here you have t, here you have sigma. And basically what you can say is that, okay, we know what have been happened in this part, so this part is known. So, and what we do is just to try to compute the expectation of what happened at this level. So we know all the past, then from here many things can happen, and this is why we take the expectation. So here, I mean, this part is fixed, and once you are here, what can happen is that the Brownian motion do the Brownian motion in different ways. So for every omega, this should happen. And so here we take the mean of all these possible values, just starting from this fixed point here. And what this property means is actually that this is the same of saying, okay, just take this value, this is bx sigma, this is small x. Take this value is random, and take it as an initial point. So just translate it here. So bx sigma omega. And now take a Brownian motion that evolves, take another one that evolves for this amount of time. So here is t minus sigma. So take t minus sigma, you arrive here, and let him evolve. So again, he can do its Brownian motion stuff, do like this, and whatever you can do. Well, if we take this expectation, these two must coincide. So at the very end, the very key property of this thing is that here does not matter what happened in the whole past. So this trajectory is fixed, is known, but it's not important. The only thing which is important to know what's happening now is what you know at the beginning. So here is this point. So no matter what happened in the story, in order to know what's happening here, for you it's fine to know what happened when you started, and then you just look at this kind of situation. And here, basically, you just reset your world, say, okay, let's start from 0, let's another system evolve in the same amount of time and initialize it with what we know at time sigma. So this is basically what Markov property means. So forget about the past, just focus on when you started to do your evolution. And this seems quite natural, but sometimes it does not work. For instance, if instead of Brownian motion, you take something which dynamics involves an integral. The integral depends on the whole path, and the path is in particular encodes the story. So if this evolution will depend of the integral of what happened before, these things does not hold anymore, because this part matters. So you cannot just erase everything, consider when you are there, and then re-let your stuff evolve. So this is a very bad way to present Markov property. Why this is useful in our case? Because we can do this computation. So let's take ux. So our case, let's take ux. This is actually this guy. Here there is this famous tower property of conditional expectation. And so we write down this guy in this way. This is a result from probability. Let's write down in this way. Given f sigma, the two things are equal, and here sigma is just the exit time of the x from the ball of radius r we introduced here in the property. So here we need to represent things in terms of this ball here. So sigma is the exit time of the Brownian motion from that ball. Then I will do a picture. So these things here, now here we use Markov property, and basically what happened is that these can be written in this way. So here we use Markov. Expectation of the same function of b2' y, and this is evaluated in y equal to bx sigma of omega. Now I will basically do a picture, but just trust me about these things. And once you do this computation by Markov property, you will realize that this is exactly what we call u of b small x sigma. And if you go back to the definition of u, this is exactly how we defined it. So, and why there is this guy, because here we start from epsilon, and then we evaluate it in this random point. Now, once we do this, the only things remain is that this guy here is just equal to the integral over the boundary of the ball, because here this guy lives on the boundary of the ball of radius r. So xr of what? Of uz times the law of this guy. This is how people write down the expectation. But this, if you go back to the very first lecture, this is the harmonic measure of a sphere, of the border of a sphere starting from the center. And thanks to the symmetry property of the Brownian motion, this is the Lebesgue measure. I mean, this is the measure, the normalized measure of that, the border, the spherical things. So this is actually what we have called pi r z. So harmonic measure of a ball starting from its center. And so that's it, because this is actually the property we want to prove, and so use harmonic. So U is harmonic. And just to conclude, just show a picture. Here you have your t, here you have your x. Then this is the ball, not a real ball, but trust me, of radius r. What we did here, and now I'm explaining what is this t prime, which was actually not so precise. Here, what we are looking for is for this. So this is b2 starting from x. And actually what we did was, let's assume to know what happened up to here. So this is sigma. And then this is the power of Markov property. So we know this is what we did by conditioning. Let's assume to know what happened up to sigma. And then let's just take another Brownian motion starting from this point. This is the sigma. And let this evolve. And now we call t prime the hitting time of the boundary of a Brownian motion starting not from small x, but from b sigma. So basically we split this trajectory, so the one that starts from x to b2, we split this into parts. So we stop at sigma and then we go there. And so this is basically the idea, and thanks to the Markov property, things becomes cool. So this is hitting time of a Brownian motion starting from b to b sigma. So we are basically iterating sort of flow property in the sense that you just start from an intermediate point and you get the same result. And okay, it's getting long, so I think that we can conclude here. This is the harmonic part. The remaining part is the continuity at the boundary, but this is a mess, and I won't go into that. But it's there where the cone condition and the fact that the points are non-trivial entering the game, and not trivial are basically not singular, is where this kind of stuff entering the game, but it's plenty of computation boring. So computation continuity at the boundary is a mess. So I won't do that. And okay, there is a final part that probably I would skip, and I will give it to the next speaker that will talk about harmonic measure, and is the fact that the harmonic measure should be seen as the Poisson kernel. So to see in the future, Poisson kernel uguale density of harmonic measure. And the Poisson kernel is just a sort of derivative of green function. This is just as a hint for maybe what will happen in the future, and is another way to relate the PD, to study the harmonic measure with PDE techniques. And okay, so I think that's it. I hope to don't have to be too much technical. So thank you for the attention. And if you have questions, please ask. Thank you.
So, is there any question? Can you please show again the notes?
Yeah. Of course, I will update that. I mean,
no, not now. Can you present again the notes? Because
okay.
When else has a question, I have a question.
Okay.
Very simple one.
Okay, but I'm not able to answer the simple stuff. Not even too complicated. Please ask.
Okay. Just before the theorem, you made kind of an example. Could you please?
Yes.
Yes. Could you please explain it again? Because I mean, I have some doubts about it. So if you could please explain it again.
Yeah, of course. I mean, here, it's an example of the singular points, and this is a way to. I presented it because the domain we are interested in, and this kind of theorem works for domain that have a boundary of regular points. And for instance, the square is of this class, so we are fine. And I mean, that example is an example of a non-regular point. And I mean, the thing is that take a circle and so here is the open ball, and you also remove the center. So basically the domain is B01 minus 0. And we want to show that x0 equal to 0 is not regular. What does it mean, not regular? Means that the probability of t d x0 equal to 0 is smaller than 1. What is t d x0? So t d x0 is the fact that first positive time, let's say, such that the Brownian motion starting from x0, it the boundary. So, and what does it mean that the probability of this guy equal to 0 is equal to 1 or smaller than 1? I mean, asking that to be equal to 1 is basically saying, okay, when you start, you already died. So when you start, you let the time just move an epsilon, then you already touch the border. So this, I don't know, it should be, it's not so easy to explain why, but this should be the case, for instance, here. If you go there, start from a point here, now one can prove that actually the probability of leaving that, I mean, from starting from that and leaving and remaining on the boundary or outside the domain, one can show that this is equal to 1. So basically, if you start from here, basically this will happen for your Brownian motion in some way. And I mean, it's quite complicated to prove, but
that is also quite counterintuitive to me. I mean, I would think that it was kind of 1/2 that probability.
Yeah, I agree. But then there is a sort of theorem that say that this kind of probability should be or 0 or 1. So at a certain point, one show that you use that kind of theorem. One argue exactly as you say, so say it's basically greater than 1/2, but then it should be 1. and that theorem is the hard part, is the 0-1 law. It's called Blumenthal 0-1 law, I think, and this is the real mess to prove, but this is actually say that this kind of event should have probability 0 or 1. And yeah, for a sort of symmetry argument, you will say, okay, it will be greater than 1/2, but then it must be 1. And so this is a regular point. This is more or less the idea, but of course, it's counterintuitive, the 0-1 law theorem. And this is a big piece of probability that not easy to tell.
Sorry,
so
those or so is the boundary included in D or
no, the boundary is outside. This is, I mean, this is the open ball minus the point.
I also have a question. The function b stochastic, how is it called, bx t, is defined only on D, or
actually no, I can go. I mean, you are looking at it as a function of what? Because if you look at it as a function of x, yeah, we say that it start. I mean, here, in order to don't have very bad stuff, we assume that the starting point is inside the domain.
But what if the function is defined only in D? What does it mean that it goes outside D? I think
no, but the function, I mean, the initial point is in D, so you start from here.
Okay. But B is defined on the whole R.
Exactly, then B just spread. You can start inside the domain, but then you can move anywhere.
Yeah, but you are staying inside of, okay, that's right.
Yeah, you can go outside and then you just say, okay, let's check when you hit this kind of point. And, or I don't know if you pass through here. Something like that.
Okay. Okay, now it's clear. Thanks. Because I thought that B was forced inside the D and it didn't make sense. But now
no, we're forcing to start inside in order to don't have many beds. I mean, one can also, in another topic is to study the opposite problem. So when you start far from a domain, so you start outside D, what happened, and if this happened that you touch this guy. Because for instance, if you start, this is why we ask that D is bounded and as nice property, because if you start from D, the sort of theorem that tells us that you will, at a certain point, touch the boundary. So at a certain point, you will exit. A little bit different is what happens if you basically leave, you start in a not bounded domain. So if you start outside, it's not so easy to say that at a certain point you will pass and touch this ball in the domain. This depends also on the dimension. It's not an easy task at all, and it's quite a complicated topic. For instance, is a no, I don't want to go too much. So yeah, it's another kind of topic.
What if you remove from the disk not just one point but another small disk? Are those points regular or not?
Like this?
Yeah.
Yeah, I think they are regular. Things becomes more complicated. I mean, a way to create like a family of, not a family, but a sort of not regular point is to take this family of disks that basically decrease to an accumulation point. This is a very bad way to build not regular point. Or another thing, which is actually related to the fact that things change depending on the dimension, is, for instance, taking a domain like this. So in this case, this is another, let's say, quite counterintuitive result. Here in dimension, if you take this point, so the center, and as a domain, you take the disk minus a line, a half line. Then in dimension 2, this guy is regular, which is strange. I mean, it's basically what you are saying is that if you start from there, basically with probability 1, you will end up, you will touch this line, which is quite counterintuitive, but is related to the fact that in dimension 2, for each point, you can take a ball and the Brownian motion will basically pass into that ball infinite times in small times. And it is a sort of property is called recurrency, I think. I don't remember the name, but it's a property of Brownian motion, which was only in dimension 2 and okay 1, but it's trivial. If you go to dimension 3, this point becomes not regular. So you start from there, and then you just come back to the domain. So no way to touch this line which belongs to the border. And so there's plenty of counterexample, pathological stuff, and the fun fact is that, okay, you can see this kind of problem from this probabilistic point of view. So you really rely on the probabilistic property of Brownian motion. And a way to prove also this kind of stuff is to relate also to Markov property, blah, blah, blah. But you can also look at this in a pure geometrical setting. So just show that you're able to build a cone which is completely included into the complementar of the domain, which for instance in dimension 2 for me is not clear at all how this will be possible to build a cone with a cone centered here, which is contained in the, I mean, not clear at all, but there is a theorem that say that the two conditions are the same, so I trust the theorem. But so yeah, there is quite plenty of result on this kind of pathological stuff. But yeah, if we are interested in the square, there is no problem. Each of these points are good. You can construct the cone outside. You can let your Brownian motion start from here, and you are sure that you will die in some way outside. That's cool.
Is there any other question? If not, we thank Mattia again. And I recall that next seminar is this Friday,